Hi everyone, this lesson covers the ANOVA, also known as the analysis of variance. First off, let's do a quick review of hypothesis testing. Hypothesis testing is the process of creating and testing the null hypothesis using inferential statistical testing. So there are 4 statistical tests we cover in this class: the t-test, the ANOVA, the chi-square, and lastly the bivariate regression analysis. In this week's lesson, we cover the ANOVA, which is also known as the analysis of variance. In any test, we're always going to test the null hypothesis, which is symbolized by H0. The null hypothesis is the hypothesis of no relationship. P-value is the likelihood that the null hypothesis is true. And so if our p-value is less than the alpha that we set, then we can reject the null hypothesis and say that there is indeed a relationship between the 2 variables that we're analyzing. Let's talk a bit about the analysis of variance. The analysis of variance compares the means of many groups at once. With the t-test, we were only allowed to compare the means of 2 groups at a single time. With the analysis of variance, we can look at a multitude of different groups and compare their means. For instance, do number of hours spent reading the news differ by religious affiliation? That is, do Catholics, Protestants, no religion affiliation have different averages in the population when it comes to reading the news? And ANOVA allows us to compare the means of the populations for more than 2 groups. Let's look at what an ANOVA would require. An ANOVA is really specific in that it requires an independent variable that is nominal or ordinal so that we can select populations from that variable. So for instance, if we selected religious affiliations, we can look at various populations of religions. If we selected perhaps social class, we can look at lower, working, middle, and upper class populations. The dependent variable, the outcome variable, has to be interval ratio because only interval ratio variables have a mean. Within any ANOVA, this is the requirement. The example we're going to look at today is religious affiliation and whether or not it influences the number of hours spent reading the news. The ANOVA measures 2 types of variation: between group and within group. The between group variation is the amount of dispersion or variation that occurs between populations. In this case, religious groups. We're going to look at Catholics, Protestants, and no religious affiliation. It also measures within group variation, and for within group variation, what's going on is we're comparing the differences between the respondents in each group. So we'll look at group 1 alone and look at the respondents and see how they differ. Now, the ANOVA checks to see whether there's more between group variation than there is within group variation, right? And so if there's more between group variation than within group variation, this leads to statistical significance. This leads to us getting closer to rejecting the null hypothesis and saying that there is a significant relationship. So the first step involved in the ANOVA is to create the hypothesis. The research hypothesis is that at least one population has a different mean than the other populations. The null hypothesis is that all of the populations are going to be the same. In this case, our research hypothesis is that at least one religious population will have a different mean of reading the news than the rest of the populations. The null hypothesis in our example is that all of the religious populations have the same mean hours of reading the news. We're going to set our alpha at 0.05. You could either set the alpha at 0.05 or 0.01. Let's take a quick look at our data. We have 6 Protestants, 7 Catholics, and 5 non-religiously affiliated individuals, and these are their number of hours spent reading the news during a given week. Here's the data that we're going to need to calculate something called the F statistic. The F statistic is going to result in a p-value, which we can then use to accept or reject the null. The data we need is the average of each sample, the sum of y for each sample, and the sum of y squared for each sample. We'll also need the grand mean, or the mean of the 3 samples combined. Let's take a look at the F-Statistic Formula now. The F-Statistic Formula looks like this. SSB stands for sum of squared between. SSW stands for sum of square within. DFB stands for degrees of freedom between, and DFW stands for degrees of freedom within. So we're going to take a look at all 4 of these different formulas. Let's first start with the SSB, which is called the between group sum of squares. Here is the formula. Let's take a minute to break this down. N sub k is the sample size of sample k standing for any of the samples that we're looking at. Sample 1, sample 2, or sample 3. Y bar sub k is the mean of sample k. Again, k stands for the sample that we are looking at. And then y bar is equal to the mean of all of the samples put together. This is also known as the grand mean. So let's take a look at what this looks like. We are going to perform this part of the equation for all 3 samples. So I have my data over to the right of me here, and so I'm going to refer back and forth to it as we fill in the information. The n for the first group is 6, so we're going to start there. And the y bar for the first group is 4.3, so we start there. We're going to subtract the grand mean of 4.7 and square the result of that. Now we're going to perform this 3 times over, so we're going to do this for the second group as well, and add all of these calculations together. So the sample size for the Catholics is 7, multiplied by 4.1 minus 4.7 squared. Lastly, the third group has a sample size of 5 with an average of 5.8. Subtract that by 4.7 and square that. The first step is to perform what's in the parentheses and square it. So now we're at 6 times 0.16. And we do the same thing for the rest of the groups. So I'm going to go ahead and do that. Okay, so this is what we end up with. Now I'm going to go ahead and multiply and add up all of the information that we have. So now I've multiplied each of those different products and obtained the following. Finally, we just add them up to get our SSB of 9.53. Let's move on to the SSW. Here is the formula for that, where the sum of y squared sub I is the sum of y squared for sample k. Again, k standing for any of these samples. The sum of yk stands for just simply the sum of y for sample k. N sub k stands for the sample size of sample k. Let's take a look at how we would perform this. Notice that we have 2 sides to the equation. Let's work on that left side first. And we actually have this information at our disposal. We have calculated the sum of y squared for each sample. The first group has a sum of y squared of 170. We're going to add that to the sum of y squared for the second group. And finally add the third group sum of y squared. We're going to subtract that by a formula we're going to perform a total of 3 times. And so that's going to look like this. We have a sum of y of 26 for the first group, and we're going to square that, then divide that by the sample size of the first group, which in this case is 6. We're going to perform the same process for the second sample. They had a sum of y of 29, so we square that and divide by the sample size of 7 Catholics. The non-religious group had a sum of y of 29 as well, but they had a sample size of 5. So I'm going to go ahead now and add up what's on the left side first. So 170 plus 177 plus 199 gets us 546. And to calculate what's going on over to the right, we're going to first square root our information and divide it by the sample size of 6 to get 112.7. Same thing for the second group. Square root of 29 gets us 841 divided by the sample size of 7 gets us 120.1. And then lastly, we have another 29 squared. This time we're dividing by the sample size of 5 to get 168.2. So we add up what's going on over to the right of us. 112.7 plus 120.1 plus 168.2 to get 401. So we have 546 minus 401 to get an SSW of 145. So these are the formulas for the DFB and DFW. The degrees of freedom between has a formula of k minus 1, where k is the number of samples. In this case, we had 3 samples, so we take 3 minus 1 to get a DFB of 2. The DFW has a formula of n minus k, where n is the total sample size. That means the combined sample size of all of the groups. In this case, we would take 6 plus 7 plus 5 to get 18. K is the number of groups, so we have 3 groups, so we end up with a DFW of 15. Now let's go ahead and plug in all of the information that we have for the F statistic. We had an SSB of 9.53. We're going to divide that by a DFB of 2. And we're going to divide the result of that by our SSW of 125 divided by a DFW of 15. So let's go ahead and do that. 9.53 divided by 2 gets us 4.765. And we're going to divide 125 by 15 to get 8.333. Okay, so let's find our F statistic. Our F statistic is 0.572. This is the distribution of F. We're going to find the critical value for F, and if our F statistic is greater than the critical value for F, then we can reject the null hypothesis. DF1 stands for DFB, the degrees of freedom between, and DF2 stands for the degrees of freedom within. So our DFB was 2, so we're going to use the column labeled 2, and our DFW was 15. So our critical F is 3.68. Our F statistic was only 0.572. So our F statistic is much smaller than the critical value for F, and therefore we cannot reject the null hypothesis. We have to accept the null hypothesis and state that there is no difference in the mean reading hours of the religious populations.